Hello friends, I'm Nikita and you are watching Prepare for GATE. Analog electronics is one of the major subjects which contains around 5 to 10 marks questions every year in GATE examination paper. Moving on with the syllabus of analog electronics, which varies from BJT, diodes, MOSFETs and their applications. Today, the topic to be discussed will be small signal equivalent circuits of diodes, simple diode, clipping, clamping, rectifier, voltage reference circuits, power supplies, ripple removal and regulation. A semiconductor diode is an electrical device which comprises of two regions, one P region and other N region, which conjointly form a PN junction. The diode works as short circuit when the device is forward biased and open circuit when the device is reverse biased in ideal conditions. However, in practical condition, there is always some threshold voltage or inside the diode, which is the built-in voltage, which only after overcoming that amount of voltage, the diode start conducting. Here you can look the basic form of a PN junction, P and N region. They are joined together and the diode behaves like a short circuit when the current is greater than 0 and it is in forward direction, and which behaves as open circuit when voltage is less than 0 and current is 0. Now looking at the characteristics of the diode, in ideal condition we will find that in reverse bias condition the current through the diode is 0, whereas in forward bias the current goes infinite at V0. However, in non-ideal conditions, more in the practical cases, we will find that when the diode is forward bias, it will have some amount of diode voltage that needs to be overcome before being conducted in forward bias direction. The threshold voltage is 0.7 volts for a non-ideal diode. In the reverse direction, we will see that it does have some saturation current, which is in an amount of 10 to the power minus 12 to 10 to the power minus 15 amperes. However, when the reverse bias reaches the Zener voltage minus VZK, K is for the knee current and Z is for the Zener. When it reaches beyond Zener voltage, you will observe that there won't be any increase in reverse bias voltage across the PN junction. However, the current will be increasing dramatically. So you can see that how there is a large flow of charge carriers after the Zener voltage is obtained, and there is no further increase in Zener voltage. So we have one reverse condition and we have one breakdown condition. In Zener diode operating in reverse breakdown region is termed as Zener diode. In reverse bias mode, when the input voltage equals to the Zener breakdown voltage, the diode current rises exponentially, which is termed as the knee current. For Vz is equals to Vz0 plus Iz into Rz. Looking at the characteristics of a Zener diode, we can see that in the forward direction it behaves just like a normal diode, whereas in reverse bias condition it behaves similar to the normal diode, and after the Zener voltage is achieved, the current through it rises exponentially in the negative direction, whereas the voltage across the device remains constant. Thus, it requires to maintain a constant potential across a device with increasing currents. Once the zero voltage is achieved, no further increase in voltage takes place across the device. Now, one more thing I need to point out over here, that often people are getting confused between the positive side of Zener diode and the negative side. And I must tell you that the point where there is a bar with where there is a limiter bar, then this is the plus sign and this is the minus sign. You can say it's the cathode and this one is the anode. With change in temperature, Zener diode changes, and the accurate measurement of which can be found by relation Tc is equals to del Vz upon Vz, T2 minus T1 into 100, where Tc is the Curie temperature. Now, as we have already, there are many models that we'll come across in calculating the various potential and the diode current passing through the circuit, for which the first one is the ideal diode characteristic, for which the potential across the diode is zero and current will rise infinitely across, and that will be dependent on the external circuitry of the device. In constant current voltage drop, we'll see that from these graphs that a constant potential of 0.7 volts is present near the diode, and after subtracting that potential from the actual circuit voltage, and dividing it by our resistance, we can get our current. Let's move to the next model,